Have you ever imagined what happens if a cylinder spins much faster than a sniper bullet? Imagine a rotational speed so extreme that the surrounding air feels like solid concrete. Inside these enigmatic black tubes, the deepest secrets of cosmic stellar energy are being unraveled. Hello everyone, I'm Ethan Walker and welcome to Weapon Science. In the quiet of highly guarded underground facilities, thousands of these machines work tirelessly. They separate material destined to power millions of homes or form the core of humanity's most terrifying weapons of mass destruction. It all depends on how long these machines are allowed to spin. This isn't just science fiction. This is the reality of the highest precision engineering in the modern world. Whenever we hear nuclear program or uranium enrichment, our minds jump to geopolitical conflict. But today, we'll set aside all political debates. We'll purely dissect the science, nuclear physics, and material mechanics behind this technology. We'll see how humanity has manipulated the laws of physics at an atomic level. The fundamental question is, how do you separate two objects that differ in weight by only a millionth of a gram? They are 100% identical in shape, color, and chemical properties. You can't use a sieve, chemical reactions, or ordinary magnets. This is the most brutal challenge in nuclear science, forcing scientists to create the gas centrifuge. Inside these facilities, centrifuge rotors spin at speeds beyond common sense, reaching 90,000 rotations per minute, or about 1,500 rotations per second. This speed far exceeds the speed of sound. A single tiny vibration, as small as a human hair, is enough to make this machine explode and shatter into pieces due to the massive G-force. Let's begin our journey from the very beginning of this material's discovery. It all starts in the Earth's crust. Uranium is a heavy metal found naturally in various parts of the world. In its raw form, it's often found as uraninite ore or pitch-blende crystal rocks that appear ordinary but store millions of times denser potential energy than coal or oil. However, natural uranium cannot be used directly for reactors or weapons. Why? Because uranium extracted from the Earth consists of two main isotopes. Approximately 99.3% is uranium-238 and only about 0.7% is uranium-235. These numbers, 235 and 238, refer to their atomic weight, or more precisely, the total number of protons and neutrons in their atomic nuclei. The problem is, uranium-238 is a relatively stable material and very difficult to split. If it's struck by a neutron, it tends to absorb it without producing a chain reaction. On the other hand, our star, uranium-235, is a fissile material, meaning its atomic nucleus is very fragile and easily splits when struck by a slow-moving neutron. When a U-235 atom splits, it releases enormous heat energy and ejects 2 to 3 new neutrons. These new neutrons then strike other U-235 atoms, splitting them and releasing more energy and neutrons. This is what we call a nuclear chain reaction. A deadly dance on a quantum scale happening in microfractions of a second. But remember, in the wild, U-235 only accounts for 0.7%. If we try to start a chain reaction in natural uranium, the neutrons released by the few U-235 atoms will be immediately absorbed by the dominant U-238. The reaction will die instantly, like trying to light a bonfire with soaking wet wood. No explosion, no electrical energy. Therefore, we must remove most of the U-238 and increase the concentration of U-235. This process of increasing the percentage of U-235 is literally called uranium enrichment. For civilian electricity reactors, we only need to raise the concentration to about 3 to 5%. However, to make a nuclear warhead, we need extreme purity, above 90%. So how do we separate them? In basic chemistry, we separate substances based on their chemical properties, like separating salt from water by evaporation. But U-235 and U-238 are the same element. They have the exact same number of electrons, meaning they react to other chemicals in a 100% identical way. Traditional chemistry is completely useless here. The only natural difference between them is their mass or physical weight. U-238 has 3 extra neutrons in its nucleus compared to U-235. This difference of 3 neutrons makes U-238 slightly heavier. How small is the difference? Only about 1.26%. This is like trying to separate two identical cars, because one has an extra water bottle in its trunk. Because their chemical properties are identical, the only way to separate these isotopes is by exploiting that microscopic weight difference using pure mechanical physics. We must use gravity, but Earth's gravity is too weak to separate atoms. We must create artificial gravity that is millions of times stronger. This is where the centrifuge machine enters the story. A centrifuge is a device that spins objects very quickly around a central axis, creating immense centripetal force. You might have seen simpler versions in medical labs, separating plasma from red blood cells. But medical centrifuges only spin a few thousand RPM. Uranium centrifuges must operate at the very limits of solid material strength. However, before we can spin this material in giant machines, we face a very real physical problem. Pure uranium is a very hard solid metal at room temperature. You can't put chunks of rock or solid metal into a centrifuge and expect them to separate. Solid objects lack the fluidity that allows the atoms to move freely. To separate isotopes at the molecular level using centrifugal force, the material must be in a fluid state, ideally a gas. Gas allows individual molecules to float and move independently, responding to the applied g-force. So our first engineering challenge is, how do we turn this heavy uranium metal into uranium gas? Pure uranium only boils and turns into gas at an incredibly absurd temperature of about 4,131 degrees Celsius. Trying to spin 4,000 degree gas inside a metal tube rotating tens of thousands of RPM is a suicide mission. Any material would melt instantly. We need a clever chemical solution to drastically lower uranium's boiling point to a controllable temperature. Nuclear chemists found the solution by combining uranium with the highly reactive chemical element fluorine. By gradually reacting uranium through a complex chemical process, they created a new compound called uranium hexafluoride, or UF6. This compound is the key to the entire modern nuclear enrichment industry worldwide. Why fluorine? This is a brilliant scientific detail. Fluorine in nature has only one stable isotope, fluorine-19. This means every fluorine atom in the universe has the exact same weight. When 6 fluorine atoms attach to uranium, any weight difference in the resulting UF6 molecule is 100% due to the weight difference between U235 and U238. No interfering variables. The true magic of uranium hexafluoride is its physical properties. At normal room temperature, UF6 is a white solid crystal looking like ordinary detergent powder. But if you heat it to just 56 degrees Celsius, cooler than a hot cup of coffee, these white crystals sublimate, changing directly from solid to gas. This 5-6 degrees Celsius sublimation temperature is a massive breakthrough. Now, engineers no longer have to deal with 4,000 degree temperatures. They just need to keep the piping systems and centrifuges slightly warm, and the uranium will remain in its gaseous state, ready to spin. However, don't be fooled by its convenience. This UF6 gas possesses inherent, terrifying, and deadly properties. Uranium hexafluoride gas is one of the most corrosive substances known to humankind. It will ravenously attack, oxidize, and destroy almost any type of metal, plastic, or rubber it touches. If this gas leaks into the air and reacts with even the slightest moisture, it will immediately turn into highly toxic and deadly hydrofluoric acid gas if inhaled. Therefore, the entire enrichment facility, from storage tanks, kilometers of piping, precision valves, to the inside of the centrifuges themselves, must be made of very specialized materials, typically military-grade aluminum alloys or pure nickel, passivated through a chemical coating process to prevent corrosion by UF6 gas. Besides being corrosive, the entire piping system must be extremely vacuumed before gas is introduced. No air, not a single drop of water. If even a tiny bit of water vapor remains in the pipes, UF6 gas will react and solidify back into solid crystals called uranyl fluoride. These crystals will clog microscopic pipes and destroy rapidly spinning centrifuge rotors. Imagine a grain of solid crystal suddenly forming inside a tube spinning at 90,000 revolutions per minute. That crystal would become a deadly projectile, tearing the tube walls from within. This is a nightmare for nuclear engineers. That's why uranium enrichment facilities have much stricter cleanliness and vacuum control standards than any hospital operating room. Now we have hot, stable uranium hexafluoride gas. This gas is slowly pumped out of giant heating tubes, flowing through a labyrinth of sterile aluminum pipes, ready to be injected into the heart of the facility, the gas centrifuge. In the context of Iranian technology, we're talking about an advanced generation model known as the IR6. Let's dissect the anatomy of this IR6 machine. From the outside, all you see is a long silver or gray cylindrical tube made of aluminum. This outer cylinder is about 2 meters tall, but this is just the outer protective shell, or what's called the vacuum casing. The true marvel and most precise engineering are hidden inside. If we cut open this outer shell, we'll find a second tube inside. This tube is called the rotor. The rotor is the component that actually spins, holding the uranium gas. In early generation centrifuges like the IR one, this rotor was made of high-strength aluminum alloy. But aluminum has physical limits. It will tear if spun too fast. To increase isotope separation efficiency, physics demands one absolute thing: spin the tube fast. The faster the rotor spins, the stronger the centripetal force and the cleaner the separation between U235 and U238. But when you spin a thin metal cylinder at tens of thousands of RPM, the centrifugal force pushing outwards becomes massive. Ordinary metals, even stainless steel, will stretch like a rubber band, deform, and eventually explode like a fragmentation grenade, unable to withstand their internal tension. This is called the tensile strength limit. To break through the speed limit, engineers had to turn to exotic materials. The first evolutionary step was using maraging steel. This is a super alloy steel, very low in carbon but rich in nickel, cobalt, and molybdenum. This steel is often used in ballistic missile casings and combat helicopter blades due to its extraordinary strength without being brittle. However, for the latest generation machines like the IR6, even maraging steel is being abandoned. The IR6 machine uses aerospace-grade composite materials. Carbon fiber. This isn't ordinary carbon fiber found in racing car hoods or tennis rackets. This is high-grade military carbon fiber, microscopically woven with specialized CNC machines, layer by layer, over a cylindrical mold. Each strand of carbon thread is much thinner than a human hair. But when woven in a specific helix pattern and injected with special epoxy resin, it creates a cylindrical structure whose strength-to-weight ratio surpasses the strongest steel on the planet. This jet black carbon fiber tube allows the IR6 rotor to spin far beyond the speed of sound. Because carbon fiber is so light, the IR6 rotor has lower mass inertia. This means the electric motor at the base of the machine needs less energy to spin it, and the vibrations generated during rotation are much smaller compared to metal rotors. At both ends of this carbon tube are precisely machined top and bottom covers. Right in the middle of this empty rotor tube is a stationary shaft, a small pole that does not spin. Inside this stationary pole are 3 microscopic pipe channels. The first pipe injects fresh UF6 gas mixture into the middle of the tube. The other 2 pipes have curved ends like small spoons called pitot tubes or scoops. These microscopic spoons are aerodynamically designed to scoop up the spinning gas at the top and bottom of the rotor without disturbing the overall gas flow. The angular position and shape of these scoops are among the most closely guarded secrets in centrifuge design, as even a slight aerodynamic error would create turbulence that destroys the separation process. Additionally, baffles are installed inside the rotor. These baffles guide the gas flow specifically, forcing the gas to move in a very precise circulation pattern, which we call axial countercurrent flow. Without these baffles, the gas would just spin randomly and isotopes would not accumulate at the ends of the tube. Now the machine structure is ready. The space between the outer aluminum casing and the carbon fiber rotor inside has been evacuated to an absolute vacuum. This is crucial. If there's even a speck of air in that narrow gap, air friction with the rotor spinning at supersonic speeds will generate immense heat, burning the carbon fiber rotor to ash in seconds. The high-frequency electric motor at the bottom of the machine starts up. This jet black carbon fiber rotor begins to spin, accelerating from 0, passing 10,000 revolutions per minute, breaking the sound barrier and continuing to accelerate with a barely audible high-pitched hum, until it finally stabilizes at an astonishing 90,000 rotations per minute. At this speed, the inner wall of the rotor tube experiences a force equivalent to more than 100,000 times Earth's gravity. If you placed a 5-gram coin on the inner wall of this tube, it would feel like half a ton. This is a physics inferno deliberately created to manipulate the laws of nature. It is at this moment that uranium hexafluoride gas is slowly injected into the middle of the tube. Let's slow down time and enter this tube at a molecular level. As the gas mixture is injected, UF6 molecules are immediately dragged by this artificial hurricane-like rotation. The giant centripetal force works relentlessly. Basic physics states that heavier objects will be thrown further from the center of rotation than lighter objects. Even though the difference is only 3 neutrons, a 1% difference in total molecular weight, the 100,000 G-force amplifies that tiny difference into something significant. UF6 molecules containing the slightly heavier uranium-238 isotope are gradually and surely pushed strongly towards the outer wall of the carbon fiber tube. They accumulate there, creating a high-pressure gas layer at the periphery of the wall. Meanwhile, you have 6 molecules containing the lighter valuable uranium 235 isotope don't have enough momentum to resist the push of the heavy U-238 molecules. As a result, these valuable U-235 molecules are pushed towards the central axis of the tube, closer to the stationary shaft in the middle. In the middle of this tube, the gas pressure is much lower, almost approaching a vacuum. Now we have a radial concentration gradient. U-238 at the periphery, U-235 inches the center. If we stopped here, the separation would be very small, almost useless. This centrifuge tube is only 2 meters high. The gas doesn't have enough time to separate perfectly with just radial rotation. This is where scientists apply a genius technique called the Zippe effect, named after its inventor, Gernot Zippe. The Zippe effect creates a secondary circulation system inside the spinning tube. The method is very elegant. Simply heat the bottom of the centrifuge and cool the top. Remember elementary school physics, hot air rises, cold air sinks. The same thing happens to the UF6 gas in this rotational inferno. Hot gas at the outer periphery of the tube, rich in U-238, is pushed to move downwards. Meanwhile, gas at the central axis, rich in lighter U-235, is pushed to move upwards. This vertical motion combines with the horizontal rotational motion, creating a very complex spiral vortex flow inside the tube. This axial circulation acts like a multiplier effect, amplifying the radial separation process many times over the height of the tube. The final result, at the very top of the rotor, we get a concentration of UF6 gas slightly enriched in uranium-235. This is what we call the enriched product. Conversely, at the very bottom of the rotor, we get an accumulation of gas dominated by the heavy uranium-238 isotope. This is what we call the tails, or depleted gas. This is where the microscopic scoops or pitot tubes we discussed earlier play their precise role. The pitot tube at the top carefully scoops this valuable U-235 gas, converting the kinetic energy of the spinning gas into pressure that pushes the gas out of the machine through a capillary pipe. Meanwhile, the pitot tube at the bottom scoops the U-238 waste gas and pushes it out through a different pipe. This process runs continuously, 24 hours a day, 7 days a week, non-stop. But there's a very fundamental mechanical problem I've deliberately saved until now. If a cylinder weighing several kilograms spins at 90,000 revolutions per minute, it must rest on something. If you use conventional steel ball bearings, the friction at these extreme speeds will melt the steel bearings into molten liquid in less than 5 seconds. Any lubricant, whether oil or advanced synthetic lubricants, would instantly evaporate or burn at such temperatures and rotational speeds. Furthermore, lubricant vapor would contaminate the vacuum inside the casing, eventually destroying the carbon fiber rotor due to air friction. So how do we hold this rotor so it can spin without touching anything? This is where the masterpiece of modern centrifuge engineering lies: magnetic levitation bearings. The carbon fiber rotor of the IR6 machine essentially floats in the air, held by invisible electromagnetic fields. It spins with almost no physical friction at all because it doesn't touch the walls or the top of the outer casing. Let's look at the very bottom of the rotor. This rotor rests on a very thin super hard steel needle which sits on a sapphire or corundum bearing plate. Yes, industrial sapphire. The tip of this needle has a microscopic contact point, so the friction is almost zero. This is the only physical touch point in the entire machine. This bottom needle is submerged in a small pool of special oil, kept from evaporating into the vacuum. At the bottom, there's also a flat hysteresis motor, an electromagnetic stator that uses a rotating magnetic field to drag the metal plate at the base of the rotor, forcing it to spin without physical contact, like spinning a top with a magnet from under a table. While the bottom rests on a sapphire needle, the top of the rotor floats entirely. A very strong permanent ring magnet is embedded in the top cover of the rotor. Precisely above it, attached to the stationary outer casing, is its paired ring magnet, positioned to attract each other. This magnetic attraction precisely holds the rotor upright. But permanent magnetic attraction alone isn't stable enough. Based on Earnshaw's theorem in electromagnetism, pure passive magnetic levitation will never be stable in all axes. If there's even a slight vibration, the rotor will tilt and hit the casing wall. Therefore, this system is equipped with optical or inductive position sensors that monitor the rotor's position thousands of times per second. These sensors are connected to active electromagnetic coils. If a sensor detects the rotor tilting by a millionth of a millimeter to the left, the computer immediately sends electricity to the coils on the right, pulling the rotor back to its perfect center position. This automatic correction process happens in microfractions of a second, continuously keeping the rotor stably levitated in the middle of the centrifugal storm. But the mechanical challenges aren't over. Any long cylindrical object that spins definitely has a natural resonance frequency, or what's called a critical speed. When the centrifuge accelerates its rotation from 0 towards 90,000 revolutions per minute, it will inevitably pass through several of these critical speed points. At these points, the machine will vibrate violently and naturally. If this carbon fiber rotor were a single rigid tube, these vibrations at critical speeds would instantly break it in half. To overcome this, the IR6 rotor isn't made from a single solid tube, but from several tube segments connected by flexible joints called bellows. These joints are usually made of very thin, specialized metal. Bellows act like human knee joints or shock absorbers. When the machine passes through critical speeds and starts to vibrate wildly, these flexible joints absorb the vibration energy, allowing the rotor to bend and sway slightly without breaking until it successfully passes through the danger zone and returns to smooth operation at its operational speed.